Alright, dimensionality reduction. So what it means, why we need dimensionality reduction. That's what we will be covering within this lecture. So why do we need dimensionality reduction anyway? Assume we have points in 1D, such as this one. Okay. And assume we have similar points but just in 2D. As you see, the points start splitting apart. Okay. And when we carry the points in 3D, if we add, for example, another dimension, these are basically the same points. We just added one dimension to carry the 1D to 2D. We add another dimension to carry 2D into 3D. As you see, as we add more dimensions to the data, the points split apart. Okay, this is sometimes a good thing, but usually a bad thing, because the distance metrics, such as the Minkowski distances, start losing their meaning if you have too many dimensions. Okay, that's something we call curse of dimensionality. And having a large number of dimensions in the feature space can mean that the volume of that space is very large, and in turn the points that we have in that space often represent a small and non-representative sample. This is the formal definition of curse of dimensionality. When dealing with high-dimensional data, it's often useful to reduce dimensionality by projecting the data to a lower dimensional subspace, which captures the essence of the data. That's called dimensionality reduction. So the whole idea is to catch the essence of the data. You just get rid of what's not essential. You capture the essential parts of the data. That's the definition of dimensionality reduction. Fewer input dimensions often mean correspondingly fewer parameters or a simpler structure in machine learning model, referred to as degree of freedom. A model with too many degrees of freedom is likely to overfit the training dataset and therefore may not perform well on new data. Okay. Then how do we do the dimensionality reduction? Basically, let's say we have 5 features, feature 1 to feature 5. Okay. Then we found that we can somehow combine a set of features without losing information. Let's say we found out that if we combine feature 1 and feature 2 and create a new feature called feature 6, we don't lose too much information. Okay, so instead of having feature 1, 2, 3, 4, 5, now we have feature 6, feature 3, feature 4, and feature 5. You see, instead of using 5 independent variables, we magically combined these 2 features, created a new feature called feature 6. Now we are using 4 instead of 5 independent variables. So principal component analysis is a dimensionality reduction method that's often used to reduce the dimensionality of large datasets by transforming a large set of variables into a smaller one that still contains most of the information in large sets. Okay. The trick in dimensionality reduction is to trade a little accuracy for simplicity. Just to make it more clear, in JPEG compression we have something called quality. If you use any image processing program, you most probably have seen the program asks you the quality of the JPEG compression. Okay, if the quality is 50, for example, you can basically see the mouth of a person. And as you start decreasing the quality, for example 25, you start losing some information. Okay, and as you drop the quality, you see the image gets worse and worse, and with quality equal to 2, that still looks like a mouth. Okay, it contains a lot less information than this one, but obviously the shape we were looking for is lost as well. But you see, we still carry the information. If you have good imagination, you can still call this as a mouth, right? With quality 6, that's carrying like 10% less information than this one, but the size of this data is a lot smaller. Okay, you can think this as compression ratio. If you give a high compression ratio such as this one, the image quality decreases, so we trade a little accuracy for simplicity, but the image size is smaller. Okay, that's the basic principle of principal component analysis. Principal components are new variables that are constructed as linear combinations or mixtures of the initial variables. These combinations are done in such a way that the new variables, meaning the principal components, are uncorrelated, and most of the information within the initial variables is skewed or compressed into the first components. So the first components of the principal components are a lot more important than the rest. Okay. So the idea is, for example, if you have a 10-dimensional data, you have 10 principal components, but PCA tries to put maximum possible information in the first component, and then maximum remaining information in the second, and it goes on like this, such as in this example. We have 10 dimensions or 10 independent variables, let's say. If we apply principal component analysis, we get 10 components. But as you see, the newly coming components are a lot different than the initial components, because most of the data is within the first principal components, and a lot of information is still in the second component, and it decreases gradually. Okay, the whole thing about PCA is it tries to skew all the information within the first few components, so that you can just skip this part. You can skip, for example, if you just take the first 3 components, you can just skip all other 7 components. Then you can skew your data. Okay. Just think this as you have 10-dimensional data, you would like to display this in 2D. Okay. If you want to display this in 2D, you need to somehow convert all these 10 variables into 2-dimensional data, and this is one way of doing that. You can just use the first 2 components of the data. And the idea behind principal component analysis is to find the projection of points as sparse as possible. So this is our components, this is our principal component, and as you see, once it's here, the projections are a lot sparser than the rest, and this is as dense as it gets, this one, and gets sparser, splitting apart, and once it is here, the projections are, these red points are basically getting sparser, and the line is here. Okay. So the principal components are orthogonal to each other, as we will be seeing in the examples. So this is the first principal component. This will be our second principal component. So how do you find the principal components anyway? There are very simple steps. In the first step, we standardize the data, and the aim of this step is to standardize the range of the continuous initial variables so that each one of them contributes equally to the analysis. Okay, and it's basically you find the mean value and the standard deviation, and you subtract the mean from the initial value, and you divide it into the standard deviation. And then you basically calculate a covariance matrix. Let's say we have 3-dimensional data, then we have a 3x3 covariance matrix for this data. And then out of this covariance matrix, we compute the eigenvalues and eigenvectors. Basically, the eigenvector that have the highest eigenvalue is the first principal component analysis, and the eigenvector that have the smallest eigenvalue is the lowest or the least important eigenvector. So how can we actually visualize principal components? let's say we have a data something like this. Okay, we have some points, and then we would like to find and display the principal components. The thing is, if you have two dimensions, then we have two principal components, okay? And the first principal component you can imagine as the best line passing through all these points, because it's representing most of the data, okay? And the second principal component is the vector that's orthogonal to the first principal component. That's basically the geometrical representation of principal components. Let's try to make an example in Python. So this is how we import the libraries, the required libraries. And then we will generate some random numbers, as we have seen in the slides. And let's plot them. You see, we have two-dimensional data within range -4 and 4. And within -2 and 4 in y-axis. So what we will be doing is we will use decomposition from scikit-learn, and we will be importing PCA. So for PCA, we can define number of components that we are searching for. For example, you can assign one here as well. You can just say, just give me the first principal component, or since this is a two-dimensional data, just give me two principal components. Okay. So it's again the same methodology. We have the definition, and then we have a fitting procedure, but this time we don't assign x and y values, we just assign just the x, just the independent variables, because what we are trying to do is we are trying to lower the dimension of x. Okay, let's do this, and then let's print the principal components. Since we asked for two principal components, this is our first principal component, which should carry the most of the information, and this is our second principal component, which is supposed to be orthogonal to the first principal component. And these are some commands that you can gather information. You can check the eigenvalues for the principal components, and let's try to visualize our principal components. The first principal component is this one, and this is basically the second principal component. Now let's try to see how we can use principal component analysis to make dimensionality reduction. We will be again using the same dataset, this blue dots, okay? But this time, instead of saying we want two principal components, we just want to have one principal component. We would like to reduce the dimension of the data, okay? And then we apply these commands. We had 500 points in 2D. Okay, the original X is this one. And XPCA is the elements we reduce to dimensions. Okay, and let's check the shape of XPCA. You see, instead of two dimensions in XPCA, we have just one dimension. So we squared this information, this two-dimensional information, into one dimension. Okay. Now let's try to get back from reduced dimension. The way we do this with scikit-learn is we have a function called inverse transform. Okay. By using the PCA function we created here. Okay, not just one, not any PCA function. It needs to be the PCA function you obtain the reduced dimension. You can just use the inverse transform to basically convert this one-dimensional information to two-dimensional information. And let's do that and try to plot it. You see, what we had in one dimension, if we take it back to two dimensions, it's basically the line that's representing these blobs in the best way. Okay, this is the first principal component of this data, and we basically have most of the information because these dots that we carried from one dimension to two dimensions, they are basically carrying most of the information that these 500 blue dots carry. Okay, so instead of using two dimensions, we could just use one dimension by PCA, and we could have less independent variables. That's basically the idea behind principal component analysis. So let's make another example with our usual iris dataset. Let's import our data. Now we have, let's load our data. You see, we have four independent variables: sepal length, sepal width, petal length, and petal width. Okay, and we have our target as the species of the flower. Before doing everything, we need to scale our data, and we need to convert our target variable into numerical value, because if you remember the data, we have categorical values, we have texture values within the target. So here we convert our categorical variables into numerical variables. Okay, and then we apply standard scaler in order to scale our data here. Now, instead of having four independent variables, because they're basically impossible to visualize in 3D. Okay, if we had three independent variables, we could use them as x, y, and z, and we could visualize them in 3D. But we have four independent variables, and it's impossible to visualize all four at the same time with a graph. Okay, if we had just sepal length and sepal width, we could use two-dimensional plots. If we had three independent variables, we could use three-dimensional plots. But we have four independent variables, so it's impossible to get a look at all these four independent variables at the same time. Therefore, we will reduce the dimension into two, and we will see how the data looks. Okay, so we will again import PCA from decomposition. We will be having two principal components, which means basically we are reducing the dimension from 4 to 2. Okay, let's do that. And then we will be concatenating with the newly created data frame, which contains two columns. We concatenate this with our target variable to create a final data frame. Now we have three columns in this data frame. The first two columns are principal component 1, principal component 2, and we have a target variable. Now let's try to plot this basically and see what will happen. You see, instead of sepal length, sepal width, petal length, petal width, we have new variables. Okay, principal component 1, principal component 2. We don't know basically the definitions of these guys. Okay, these are newly created components from our four independent variables. So we reduce the dimensions of our data sets from 4 to 2, and if we plot them, you see we can observe the distribution of the classes. And the good thing about this is we can basically see the contribution of all four independent variables within one plot. Okay, we could just basically plot a lot of two-dimensional things with all the combinations of the sepal length, sepal width, petal length, petal width. But instead of trying to deal with four independent variables, we can now just see the structure, the distribution of the data with our principal components. That's one good thing about the principal components. And we said we can basically reduce the dimension of the data. Let's see what our MNIST data set looks like if we reduce its dimension. In order to do that, we will be using the function I provided beforehand, just to load the training and tests data for the MNIST. So the first thing is first, we load the data, and this is our visualization function that we'll be using. Now let's try to visualize the X train. So this is a 9. Okay. And let's see the Y train. This confirms that this is a 9 as well. And this 9 looks like this. Remember, the MNIST database was containing images with pixel values of 28 by 28. That's a pretty small image, but anyhow, it basically represents a 9. Okay, now let's flatten our train and test sets. And then let's scale them so that we can use principal components analysis within that. Okay, let's check the shape of our data for the training images. So in training sets, we have 60,000 images, remember. And since each image contains 28 by 28 pixels, we have 784 independent variables for each image. Okay, and we will be trying to reduce this number. So we are going to try to compress the image, to say. Okay, here is a different usage for principal component analysis. We just say make an instance of the model that preserves 95% of the data. That's what it says. Okay, the principal component analysis. This is something specific to the scikit-learn. And we create a PCA model with our training images. That may take a little bit time. Now we have a PCA trained. Now we will use PCA transform to convert our training as well as test images into a reduced dimension. Okay, let's do that. And then let's check the shape of our newly generated images. You see, instead of having 784 dimensions, now we have 331 dimensions. Okay, this is a more compressed information than this. Obviously, we lost some of the data. We lost like 5% of the data, but now we have a lot fewer dimensions with that. Okay, that's why it's called dimensionality reduction, basically. Now let's transform these guys back to see how much information we lost when we are doing classification. Okay, so remember, inverse transform will carry our 331 dimensions into 784 dimensions. Let's try to do that. Now we have again our classical images 28 by 28. Let's flatten them. We will train some classifiers to see whether we lost any accuracy by doing dimensionality reduction. Now let's try to visualize the original image. This is the 600 image from X train, and this is going to be the 600 image from our newly generated data that we created from the dimensionality reduction set. Okay, you see, it still looks like a 9. It's not bad, actually. It's pretty good from my point of view, because we kept 95% of the information. We just neglected 5% of the information, and as you see, that 5% of the information was not very important. We could recover this 9 from our dimensional reduction set. And remember, from 700 dimensions, we reduced it to 300 dimensions. Once we carry these 300 dimensions to 700 dimensions, we are still capable of recovering our image. So that's basically how JPEG compression works as well. Most of the compressions work. They reduce the dimensions, and they use basically a compression ratio. If this compression ratio is too high, they reduce the dimensions in a way that they contain less information. And if the compression ratio is less, then we keep most of the dimensions from the original data. Now let's try to see whether the dimensionality reduction affected a classifier too much. We will train a logistic regression classifier, and we will create 2 regressors, one with principal component analysis, one without principal component analysis. Okay. We didn't use support vector machines because we would like to have it a little bit quicker. You can try different classifiers with this example. We will basically fit the principal component analysis data, and you see we have a score of 92%. Okay, when we have principal component analysis. Let's try to do the same with without PCA. Okay. So we trained a logistic regression model with our training images with PCA, and then we used basically the test images with PCA, and we obtained an accuracy of this number. Okay. Now we trained a logistic regressor, but without principal component analysis. Okay, and now we will check the accuracy. You see it's more or less the same. So that concludes our dimensionality reduction lecture. We have seen we can basically reduce the dimension of data by preserving most of the data. And the idea behind principal components is it creates new components or new variables that contains most of the information in the first components. Okay, so that was it for the dimensionality reduction.